Welcome to this session on the Erasmus Plus course, which is a recorded lecture, mainly because many of you are busy with exams, so there was no way we could avoid this. And this lecture about neural networks, which is our next topic, is now just a recorded lecture. So I hope you can get something out of the video here. And then we will have a new session on Friday, December the 16th, from 10 to 12 in the morning. And that session will continue the discussion of neural networks. So please feel free to watch the video before you come back on the December the 16th. And we will also discuss parts of project number 1, which has a deadline by the end of January. Now, the setup for the sessions which we will have in January is something which we need to discuss a little bit later. But most likely, we will have 4 to 5 sessions in the week, which begins with January the 9th. And probably we'll also have 1 or 2 more sessions the week thereafter. And then we should basically be done with all the material which is needed for project number 2. So we will come back to a more finalized schedule a little bit later. Now, neural networks is our first encounter with deep learning methods. And deep learning methods are methods which really pervade the machine learning literature. There is a very, very important theorem, which is called the universal approximation theorem, which we are going to use again and again and again. And this theorem states that you can approximate a continuous function to a given precision or given error with at least one hidden layer. Now, one hidden layer is something which we are going to discuss a little bit later now today, when we are looking at the structure and the setup of a neural network. And one hidden layer is a layer which then will have different nodes or neurons or units which connect an input layer where we have the variables x as we have defined them earlier, which then feed in an input, and then through the hidden layer you will produce an output, and this output, which then will depend on the architecture of the network, that output will be compared with the output which you have from your data. So that is a process which is going to be solved in an iterative way, where we try to improve the training of the model again and again till we have a result, an output from our model and the neural network, which then agrees to a given precision with the data which we want to reproduce. So we are still going to have a supervised learning case. We are going to have input data, and we're going to have output data, or data which we are going to call for the target. So these are the data which are given and which we want to reproduce with a given model. If you think back to standard linear regression or logistic regression, which we discussed in the previous weeks, these are cases or methods where you would typically fit a given function, which would then define your model in order to reproduce some data which you have access to. So what we are going to see now is that a neural network is actually going to play the role of, let's say, standard linear regression methods like ordinary least squares or ridge regression. And the model complexity now is going to be given by the architecture of the neural network. So the architecture is going to contain parameters, which we are going to call hidden, the number of hidden layers. Every hidden layer will have a given set of nodes. So these will also be parameters and parts of the architecture and thereby the model. When we produce an output from a given node or neuron, as we will call them interchangeably, then this output is normally given by the output of a function which is called an activation function. The type of activation functions will also be part of the model which we will construct. Then we will also have different types of ways of calculating the gradients, because we're going to optimize parameters. and the parameters are going to be weights and biases over a neural network. Now, when we do the training, we have to calculate gradients, and these gradients will then be evaluated with the methods which we have discussed under the optimization chapters and discussions in the previous lectures. So the optimization approaches which we are going to use are methods like adaptive gradient, ADAM, the root mean square propagation, or RMS prop as we shortened it to, and many other the methods which we encountered when we looked at gradient descent and stochastic gradient descent. Then finally, the data which we have, they will obviously be compared, or the data which are produced by the network, they are going to be compared with the final target values. So what we're going to do now, before we continue with the slides here and our Jupyter notebooks, we are going to slow down the pace a little bit, and we're going to define some of the basic quantities on the whiteboard here. So let's dive into the whiteboard and take a quick look at some of the basic parameters which we are going to use in order to define a neural network. So if we now look back a little bit to what we have done, suppose now that we consider a very simple case where we have an input x1 and x2, these are two variables, and then we have a given output. So consider now the following. So we have an input which is now given by two variables. So these could be vectors with a given number of input parameters, but let's just label them as x1 and x2. And then we have an output which we previously have labeled with a y, but this y could now be, it can be a vector, but we are going to relabel this in terms of a variable t, and t stands for target. So these are the values which we want to target and the values which we want our model to reproduce. So what happens now is that if we write this in a graphical way, we have these incoming variables, x1 and x2 here. Now this is then modulated by some function. So we take a function which in a way represents our model. It could also be a function which exists, which reproduces our data. So this produces an output, and we are now going simply to call this output y. And previously, we called this y tilde, but now we're just going to call it y. This is now going to be compared. So here there will be some kind of cost function. And this could be a classification problem, or it could be a standard regression problem where we are fitting a specific function. So we are going to label this in this way. So there will be a target t, which we are going to compare with this output value y. Now, we could now think of this being given by some kind of model. So we are going to replace this function f, this x1 and x2 here. This is going to be replaced by a function which I will simply now label as a function sigma. And this is going to take a name in the neural network terminology, which we're going to call for an activation function. And this is going to be a function of a variable x1. There's going to be a variable x2, obviously. These are the input variables. And these variables are going to be modulated by a weight w1, a weight w2, and then there's going to be a parameter which we're going to call for a bias. And normally we would rewrite this in terms of a vector x, which contains x1, x2, or this could be our design matrix. So we're not going to be specific now about whether x is a matrix like the design matrix, or whether this is a vector which just contains two entries, x1 and x2. And then we are now going to look at all the possible parameters of our theory in terms of a variable theta. So this theta is now going to contain these weights. So above we put them, we gave them the variables W1 and W2 here, and this parameter B, which we are going to call for the bias. So if we now look at this case which we have here, this is going to represent the weights. And this term here is normally referred to as the bias. So previously, we used the label beta for the parameters, the unknown parameters. Now we're going to introduce a little bit more parameters. And one possible function which we could set up then could be a function sigma of x1, x2, w1, w2 equal beta. And this could simply be a function which is given by the input x1, which is then modulated by this weight w1, plus some x2, which is then modulated by this weight w2, plus some b. And this is something which we want to be equal to the output from our network. So the idea now is to find a model which reproduces the observables t, the target, which in our case is given by this variable y. And we want this function to actually produce correctly the target data t. So we can rewrite this in a more compact way. We could now rewrite everything in terms of a vector x. If we think of the vector transpose, so this is x1 and x2 here. And then we would have a new vector w, which is given by w1 and w2 here. And this gives us now a model for this function sigma of x, and then we can write it in a more compact way in terms of these parameters theta, which now will be given by a vector x of t. And now we could think of this being a specific instance I. So this is a target which we want to reproduce, a given observation I. So we would have a vector x of I here, and this is multiplied with the weights, plus b, and this is going to be equal over y of I. And obviously we want this to be equal to the target t of I. That's the value we want to reproduce. So in essence, the way we are going to define these kind of networks are now being based on a model which contains some parameters w's and a set of parameters b. If you're thinking of this as a function you want to use to reproduce a data set, or suppose now if we go back to the classification problem we looked at earlier, and if we now take a data set with x1 and x2, and where the target t of I is either equal to -1 or +1, so we have only two values. So this is a binary classification problem. And you could now think that x1 corresponds to the number of hours we study, and x2 to the number of hours we sleep. And then we are going to plot the t of i's in terms of you obtaining a grade which is below the average or above the average. So if we take t of I equal to +1, you then have a grade which is above the average. If you have t I equal to -1, you have a grade which is below the average. And suppose now below average is given by the crosses here, and above average is given by the circles here. Now, if we would use linear regression here, we could think of fitting a line which separates the two sets of observations. So you could now think of us making a linear regression fit, and then simply finding a line which separates the two classes. And then what you would say then, if in this specific case we are fitting a function sigma x of, and with these parameters theta, which now on the line is equal to 0. So if the result is larger than 0, then you have a grade which is above the average. If the value is below 0, then you have a grade which is below average. So you could now think of fitting a line where the output is equal to 0. And then you would simply say that, okay, if it's above 0, then we have a grade which is better than the average, and below, worse than the average. So this is one of many, many possibilities. And then this parameter b, which we have called the bias, this parameter b is something you could think of the intercept here. And then we have a dependence on the parameters x1 and x2, and we fit the function to reproduce the data, and then we obtain the parameters w1, w2, and b. And then we are done. Now, this is a pretty simple case where the dependence on the unknown parameters w and b is given by a linear function. So if we have a linear problem like this, then life is pretty simple, and we could actually revert to logistic regression or just to a standard linear regression case. Later, we will see when we jump into the field of support vector machines is that there will actually be many lines which can be used to separate the two classes here. And this is not the optimal way of proceeding. Actually, the optimal way of proceeding here, if you have these well-separated classes, is to use something which is called support vector machines, which is another popular method, which at the end leads to a convex optimization problem. And we are going to discuss that after the winter break here. So for this specific case, we have now a well-defined case. So let's now try to look at some other examples where this kind of linear behavior may actually fail miserably. So if you look back at what we had here, and we look back at this drawing here, this is a simple case where we have assumed that we have a simple linear dependence. And we would then have what we going to call here a node or a neuron. This actually has a name in the literature and is normally called the simple perceptron model or the single perceptron model. And the perceptron naming comes back from neuroscience, which inspired a lot of these mathematical models. And the reason why they're called neural networks is that you could think of every node here, as we call them, as a neuron, and the neuron receives an input x1 and x2, and depending on how it's modulated, depending on the physical processes taking place in the neuron, it emits an output y. So much of the naming here is inspired from neuroscience. I am going mostly to call these neurons for nodes. I normally prefer that name, but I may interchangeably and without being aware of it, may also call them neurons or even units. The name activation function, which we used for this function f, which we rewrote in terms of a sigma, comes also from neuron science, because you could now think of x1 and x2 being inputs which are fed into the neuron, and then this passes through a function which then produces an output or an activation of further neurons or nodes at a later stage. So we normally call this for an activation function, and this has stuck in the literature. So, but let's now look at another example and see whether we can actually continue along this simple line where we can get away with a simple classification problem where we have just two well-defined classes, or whether we could do a regression problem. So the case we're going to look at now is something which is called an OR gate. Now, in this particular case, we have an input, two inputs, x1 and x2, and then we get an output t here. So this is the target. Now, what happens in this case, when we make a table, we would have a bit 0 and bit 1. So if we have a bit 0 coming in and a bit 0, then the output is a bit 0. If I have 0 and 1, then the output is 1. If I have 1 and 0, the output is 1. And if I have 1 and 1, the output is 1. So this is an OR gate, and many of you are probably familiar with this type of gates from electronics. Now, if we make a plot of this now, the plot is actually going to tell us that most likely we could now use a simple classification problem with logistic regression, or we could even fit a straight line which separates the two faces. So if we now look at the way we can write this, we have now the following. So we have a vector 0, 0. So this is transposed now, obviously. And we have 0, 1. So these are the input data of t when we now relate to what we did previously. And finally, we have a 1 and 1. If we make a plot of this now, we have two entries in both cases. So we have x1 along the x-axis and x2 along the y-axis. We have 0 and 1. And we know that when we have 0 and 1, we get a 1. When we have 1 and 1, we get a 1. And then when we have 0 and 1, we get a 1 here. But then we have a circle here, which we're going to blacken. And then this gives us a 0. Now, if you think back to the simple case which we had here, you see now that we could even be tempted to fit a straight line here. So you could think of us setting up a straight line which goes through the domain of events like this, or domain of outputs in this specific way. And then we could just use either logistic regression, since this is a binary classification problem, or we could simply have just fit a line with linear regression in order to separate the two classes here. So this is a pretty well-defined problem. Now, there's another gate, which is called an AND gate, which is also pretty easy to set up. And the AND gate is a gate which now allows us to have a similar domain, except that then we will have results which with 3 zeros and just 1. And in that case, we can also separate things by using, let's say, logistic regression, or we could just use linear regression again. But there's another gate which is going to be a little bit more problematic, and that's the XOR gate. So let's look at the inputs and the outputs to that specific gate. So the inputs are going to be the same, but the outputs will be different. So we have the X1s and the X2s, and then we have the target. So when we have 0, 0, then the target is 0. So that's the output, or what we previously called for Y. And then I have a 0, 1, and this gives me 1. I have 1, 0, and that gives me 1. So this is called an exclusive OR gate. And if I have 1, 1, I actually get 0. Now, in this particular case, if I make a plot of the possible targets which we have, and we still have a plot with the x1 along the x-axis and x2 along the y-axis, we have a 0 and 1. These are the inputs, and 0 and 1. Now, what happens now is that we have a 0 here, and then we have a 0 here, and then we have a 1 here. That's the open circle. So the zeros are the zeros. The open circles are the ones, and the filled circles are the zeros. Now, in this case, you see immediately that you cannot find a simple line which separates the two classes here. And the two classes are given by either the filled circles or the open circles. So if you put a line in here, you will miss one of the observations. If you put a line in here, you will miss one of the observations. And similarly, if you put lines in all of the places here, you will actually miss the different observations. So this is an example of where this kind of linear model, which we could use here in this particular case, and simply assume that we could reproduce the target data by using such a simple linear dependence in terms of the unknown parameters W and the intercept here B, or this specific case which we had here, that one. This is now a case where we cannot use this plain linear dependence on the unknown parameters. And this is actually where a simple neural network with one hidden layer is going to do the job for us. So as you will see a little bit later, with one hidden layer, we're actually going to be able to reproduce this specific situation here, given by the exclusive OR gate. Now, let's take a closer look here at what we have and look at the mathematics. So if we look at the parameter theta, and we write that as a vector, that is going to contain B, it's going to contain W1 and W2. So this is one specific way by which we can encode the parameters which we have. So if we now look at the OR gate, so let's take a closer look at that and try to study the OR gate with just linear regression, as we did before. So if we look at that case, what we would have now is a vector 0, 0, which is then multiplied with W1 and W2 here. That's the weights, plus B, and that's going to be equal to a target T, which we want to be equal to 0. So it's actually pretty easy to set up everything here and run through the calculations. And we have W1, W2 here, plus B, and that's going to give us a target now, which is equal to 1. So I use this as a way to repeat what we've also been discussing in connection with both linear regression and logistic regression. And we want this one to be equal to 1. That's a target we want to reproduce. We have a 1, 1, and then we have a W1 and a W2 here, plus a B, and that's equal to 1 again. And it's pretty straightforward then to see that your design matrix is going to look as follows. So you will have ones here, so they're going to represent the intercept. And then you have x1 and x2, and we know that x1 could be 0, x2 could be 0, and then we are looking at the cases where x1 is 0, x2 is 1, and then we have 1 and 0, and 1 and 1. So these are our inputs, which we have been coding now. And we insist on having this intercept. Then, if we insist again on linear regression here, we get that x transpose times x. If we calculate it, we are going to get 4, 2, and 2, 2, 2, and 1. And then we have 2, 1, 2, like this. And then we can take the inverse of that quantity. And we know then that the parameters theta, which we previously labeled as beta, and we're going to put a hat on them, they're going to be given by the inverse of this matrix, which is pretty easy to evaluate, multiplied with x transpose times y. And what we will be getting then is the following. So we will have a parameter 1/2. We have a 0 and a 0, and the transpose in here. So in case we now have, so this is basically linear regression, and we find the optimal parameters. Now we haven't said anything about the values of the target, because what we want then is obviously to take y. This is what we are going to make as a prediction with this specific model. So we're going to take the design matrix, and then we need to multiply this with theta, or beta, as we called them before. And this is essentially us now taking the design matrix, which has 1, 1, 1, and then 1 again, and then 0, 0, 0, 1, 1, 0, 1, 1, and then multiply it with this vector which we have here, which is 1/2, 0, and 0. So these are the parameters. Now what we get then for that specific case is the following. So we get a y. Oh, sorry, I actually wrote down the wrong result for you guys. So what we had, so let me just change this. Actually, that was another result. So I get 1 divided by 4, and I have 1/2 and 1/2 for the values for the OR gate. Now that means the following. So I get now for the OR gate, I get a result y, which is now given in terms of a vector, and I'm going to look at y transposed, which is 1 divided by 4, 3 divided by 4, 3 divided, this is the prediction I'm going to make, and 5 divided by 4. Now the target which we want, transposed, is equal to 0. And then it's given by 1, 1, and 1. Now, remember now that we are fitting a straight line. So the prediction which we are going to make with a straight line here says that in one case it's 1 divided by 4, and in another case it's 3 divided by 4, 3 divided by 4, and 5 divided by 4. So what we could say now is that if our prediction is less than 0.5, we put it to 0. So if the prediction less than 0.5, then our prediction is equal to 0. So we are not going to reproduce 0, 1, 1, 1, but we're actually going to make a prediction, because now we are fitting a straight line. And this simply says now that we have to make a decision, and we would simply say now if it's less than 0.5, it's 0. If it's larger, it's 1. And you see now with this kind of fit of a straight line which separates the data, we make a correct prediction. Now, if I take an XOR gate, which has a different type of targets which we're going to reproduce, because then the targets are going to be given by 0, 1, 1, 0. In that specific case, I'm going to get the following parameters. So I will get theta vector equal to the optimal parameters equal to a half, 0, and 0. Now, when I then make a prediction here, my prediction for the XOR gate is now going to be given by the following numbers. So I'm going to have a prediction here where all the numbers, when I multiply with the design matrix, I will get 0.5 for all the cases. But the target which I want to produce is 0, 1, 1, and 0. And you see that in this case, if I now say that if my prediction is less than a half, then I should have 0. If it's larger than a half, it should be equal to 1. But in my case, all my predictions are equal to a half. So you could now simply say that we fail with this simple linear model. So for the XOR gate, what we actually are going to need, and we can show that this is possible, we need to have a more complex model which takes into account nonlinearity. And you can see directly from the graph which we had here that there has to be a nonlinearity in terms of the unknown parameters W1 and W2, because we are not able to separate the two classes with a straight line. If we could separate them by a straight line, this would be just a walk in the park, and we would just have a simple linear dependence in terms of the unknown parameters W. So we need to have a more complex model which bakes in some nonlinearity. With nonlinearity, and this is something which we can achieve with a simple neural network with just one hidden layer. And we will demonstrate this through some calculations a little bit later. So we can achieve this with a simple neural network with one hidden layer. So now we need to demystify a little bit what is meant with a hidden layer. So let's look back at the perceptron model, what we call the simple or the single perceptron model. Now we are going to change this. So we are going to define an input layer. And this input layer is going to have the same inputs which we had before. So it's going to be an X1 and an X2 here. Now this input feeds in to a hidden layer And this hidden layer is now going to have, in our specific case, it's going to be a model with two nodes, so which we are going to call for an H1 and an H2 here. So this input which we have is now being modulated. So this is our input layer. And we are going to write it down in terms of the input nodes. Now this input is now fed into this hidden node, but it also feeds into this hidden node. So we are saying now that the input layer, all the nodes in input layer are connected with all the nodes in the hidden layer. However, we are not going to look at connections between the nodes in each layer. This is now being modulated with a weight, which I'm going to call W11. This is going to be a weight W12 here. And finally, there's going to be a W21 here, and then a connection here, which we're going to call W22 here. Now, each of these nodes are going to conspire in producing an output. So this specific node, H1, which we have here, this is going to produce an output, which I'm going to just call for A1 for later use. And this is going to have a node, which is an output, which is being called A2. And they conspire, since we have only one output here, there's going to be a final layer here. And that has one node in this specific case because we have only one output. So this outputs a final Y for this specific case. And we want to compare that with, through a given cost function. So this is where the cost function comes in, with the targets. So this is going to be our cost function. And that's where we are going to make the evaluation or test the quality of the model by comparing the output which we have produced from the network with the target values. So this is also going to produce a output. And I'm going to put labels here. So there's only one hidden layer in this case. So this is going to have a label 1, a label 1. And this produces an output A of L, the final layer, which is equal to Y. So I'm just bringing up these different types of notations here because we are going to use them in the derivations of the algorithm for finding the optimal values for the weights and the biases. So this is normally called the output layer. In here, we are going to have these biases. So there could be a B2, and there could also be a bias here, B1. And in here, and we're going to put labels on them. So this is the bias for the hidden layer. And this is going to be to have a bias for the last layer, which I'm going to label with an uppercase L. So this is the basic structure of a neural network. Now you can have many more nodes, you can have many more layers. That will just change the architecture of the network. So the unknown parameters now are these different biases and weights. Now you should also keep in mind here that we are going to have a weight here. So there will be a weight 1 here. We are going to put a label 1 because these are the elements of a matrix in this case, which refer to the first hidden layer. And in this specific case, we're going to have a label L. And similarly here, this A2 is going to be modulated with a new weight. So if you now do the counting, you will see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9 parameters which we need to define in this specific model. So these will be the unknown parameters. Now, the way you would typically train such a network to find the optimal parameters is to have a feed-forward stage. With initialized values, initial values for the weights and the biases, for weights and biases, And we normally keep these biases. The main reason for why we do that is that if by accident these weights are 0, then we are multiplying with zeros, and the training of the parameters will stop. So the biases, if we give them a small non-zero value, they will ensure that the training of the network may not stop. So we would then have a feed-forward stage where we start from the input layer and we feed forward till we reach the output layer. Then we compare the output which we have produced with the targets. And this comparison is done by evaluating the cost function. And then we take the gradient of the cost function, and we want typically to reduce that gradient or to minimize the cost function. The next stage in this training is given by a feed backward or a backward propagation. Propagation to update the weights and the biases, to update the parameters, theta. So I'm just going to write it in terms of the collective container, the parameters given by this collective variable theta, which now contains our weights and the biases. So now I'm just writing this in a very generic way here. Then we would repeat this process, repeat 1 and 2, till, let's say, if you want to minimize the cost function, till the cost function at the output doesn't change by a quantity which you have fixed, till we reach convergence. So you can see now that this is an iterative process where we are going to go back and forth. And the backward propagation is, and this is something I wanted to say a little bit about. So the backward propagation is the algorithm which is normally used. Backward propagation is a usage of the chain rule. It's a systematic and repeated usage of the chain rule in order to update the gradients and thereby the parameters W and B. In order to compute gradients, and find the optimal parameters theta. Now, backward propagation is the same. So I'm going to put equality sign here. Is the same as reverse mode, and this is something which we are going to discuss in the new year, during the new year. This is the same as reverse mode in automatic differentiation. And I will try to explain to you a little bit later why back propagation is better to do than a forward propagation in order to find the weights and the biases. And you will see that from the setup of a neural network, why the reverse mode in the algorithm automatic differentiation is equivalent with the backward propagation algorithm. So what we are going to do a little bit later now, after some simple explorations and the discussions of these simple examples with the OR gate and the exclusive OR gate, we are then going to set up the backward propagation algorithm. And the backward propagation algorithm is going to give us the analytical expression for the gradients. And we are going to calculate the gradients with the standard methods which we have explored till now. So this would be stochastic gradient descent with batches, and with the adaptive learning rates given by methods like adaptive gradient, root mean square propagation, and many of the other methods which we have encountered. But now we're going to take a small break. And after the break, we are going to look at some simple examples and see how we can implement this OR gate and XOR gate using, let's say, just plain linear regression, logistic regression, and then we will show that a neural network with at least one hidden layer is going to give us the correct results. So what we can do now is to try to write this graph for the neural network in a more compact way. And this is the type of ways which you will often encounter. And you would typically see this written in the following way. So in our case, we have just two inputs. So these are the input nodes, x1 and x2 here. And then we have a hidden layer, which we mark with a sigma here, which now is the represents this activation function. And there is an input b, which is given by the bias. So here we now have a modulation of the results. So we have this weight matrix, which we have in here. And then this produces an output. It can produce more than just one output. This is fed into the so-called output layer. And we would normally label this with a y, not a y tilde. And this is then compared where we have the cost function here with the target values. And this is our output layer, which then feeds in a result to the cost function. And this quantity sigma is a function of x, the inputs, and these unknown parameters theta. And it's normally called an activation function. There are many types of activation functions, and one of them is a function which many of you have met already, which is the sigmoid function, which is widely used. You could even have a step function, which means that if the value is less than a certain threshold, it just 0 as an output, or if it's larger than a certain threshold, it just outputs 1, just to give you an example. We are coming back to these things. But let's take a close look at the Jupyter notebooks and see how we can simulate this OR gate, exclusive OR gate, or even an AND gate, and see what happens when we use logistic regression, linear regression, and finally, a neural network with a hidden layer. So let's take a closer look at that. So we need now to dive into the Jupyter notebook. And in the Jupyter notebook for these days, what you will find is first a simple setup of the exclusive OR, the OR gate, and the AND gates. So as we discussed before the small break we had, the design matrix is now given by these entries. So we have 1 for the intercept, which represent this parameter b. And then we have the x's, which are 0, 0, 0, 1, 1, 0, 1, 1. So the design matrix stays the same all the time. Now, if I now look at the exclusive OR gate, that has an output which is 0, 1, 1, and 0. And now you know that the parameters, the theta for the exclusive OR gate has to be given by the inverse of the design matrix, which we have here. So that's the design matrix transpose times the design matrix, and then we calculate the inverse of that one. And then this is multiplied with the y values, the transpose design matrix times the y values here. And this is the same as we've seen before. We can do the same with the OR gate. It's again exactly the same thing. And then we can also have an AND gate where the values, the outputs are 0, 0, and 1. And what you would see then is the following, is that the linear regression prediction for the OR gate is 0.25, 75, 0.75, and 1.25. So if it's larger than 0.5, it's 1. If it's less, it's 0. So linear regression allows us to fit a line, which makes a perfect fit to the data. The same thing happens with the AND gate. So in the AND gates, if it's less than 0.5, it's 0. If it's larger than 0.5, it's 1, which is also the value for an AND gate. And now you see that for the exclusive OR gate, we're just getting a same prediction for all the cases, which means that we just have a 50, it's going to be converted to 50-50 case. So we can repeat this and do logistic regression. So I'm just calling the logistic regression code here with the scikit-learn. I do a log-reg fit. I take my OR gate. I take my exclusive OR gate, and then I have my AND gate. And in all cases, the design matrix is always the same. And then I can actually fit things here. And if you scroll down a little bit, you will now see that my prediction or the accuracy, so I'm just counting the number of correctly evaluated events with the OR gate is 0.75. With the exclusive OR gate, it's just 50%. Whereas for the AND gate is 75%, which is also not very impressive. So we still fail miserably with these kind of linear models. So remember now that logistic regression has also, when we take the ratios of the probability, it gives a linear dependence on the unknown parameters. So we are actually not getting something which is very impressive. Now, what I've done here is simply to make a classification problem using the multi-layer perceptron model and classifier which scikit-learn has. So, and later we're actually going to do this with our own functions. So the multi-layer perceptron classifier, in this specific case, we make a fit here, and then I calculate the predictions which I make, and then I calculate the score. So the score in this case, if it's equal to 1, it means that we simply count the number of cases which are correctly classified and divide that with the number of cases which we have. So that means if you get a score, like here, the accuracy, which is equal to 1, it means you have classified all events correctly. So in this case, the neural network is just a black box for us. And being a black box is not exactly what is the philosophy behind this course. So what we're going to do now is try to demystify a little bit of the basic setups of a neural network. And that is going to lead us to the back propagation algorithm. So if you think of the mathematical model which we have done, and I'm going to introduce some of the concepts here. So if we had this simple multi-perceptron layer model, we had just some weights here multiplied with the input variables x plus the b's, and then everything was modulated with a function f, which we also call for sigma. And then our output y is now given by these quantities here. So z is simply the argument, the sum over all these quantities, and that defines the argument to this function f. So this would be the typical thing which we would have for a single layer. Now what you could do now is to introduce a hidden layer, and then every node in the hidden layer would have a input to that node in the hidden layer. So I'm putting a 1 here to indicate that that's a node in hidden layer number 1, and this is node I, and this takes these modulated weights, these weights which modulate the input, plus this bias. And if we scroll down, that means that we will have an output 1. This is the output from node I, from layer 1, the hidden layer, which is simply given by this argument here. And I can continue like this. And the number of which you have here, this n, is a number which runs over all the nodes which you would have in a specific layer. And we are coming back to that a little bit later. So if you keep repeating this, you can see now that you can rewrite this in terms of the output of a neuron I in a second layer, which would simply be given by this. And this function here now depends on the previous function. So the output here, this y of I here, is now simply given by this function from the previous layer, and then plus these weights here. No, sorry, the bias here. And if I do a 3 layers, this is actually going to be rewritten like this. And the mathematical model is that I get all this nested set of multiplications of matrices and vectors. And this is what is going to give us the nonlinearity. So having this function f, which you see here, this ensures with one hidden layer that we can account for the nonlinearity, which will allow us to, for instance, predict correctly the exclusive OR gate. So this nonlinearity is something which is ensured by these mathematical operations, which are affine transformations Basically, these are matrix multiplications. So you can see that easily here, because every time we do this operation, this f of 2, if we just have a simplified case where we have a 3 by 3 setup here for the matrix W, this f2 now is going to contain this matrix multiplied with the vectors here. And this is then we add to this the bias vectors. So in this kind of notation, what we have now is typically that a specific node receives a specific input, which would then correspond to one specific row here multiplied with a column vector y, which now contains the outputs from the previous hidden layer. And this way we can just continue. So what you will see now is that we are going to have a series of affine transformations where we take a dense net actually. So all the layers are connected. All the nodes from one layer are connected with the nodes in the next layer. And that means that what we end up with doing then is to have matrix vector multiplications and matrix multiplications. This is the basic mathematics of a neural network. This would then make up the feed-forward pass in a neural network. So we are coming back to some of the mathematics of neural networks a little bit later. But now what we want to do is to set up some of the basic mathematical operations which are needed in order to set up what we call the backpropagation algorithm. So there are many such functions which we have just labeled as a f here. We have some requirements to them. They have to be continuous. We want them to be non-constant. We want them to bounded. They should be monotonic or increasing. And it should be easy to calculate the derivatives of these functions. And one very popular one is the sigmoid function, which we have encountered already. We have also the tan h function. And then we have a whole plethora of functions like the rectified linear unit, we have the exponential linear unit, etc., etc., etc. So there is nothing, specific with some of these functions, except that some of them, for historical reasons, have been widely used. So the sigmoid function is a function, the S-shaped function was one of the first functions which was used to describe properties of neurons in neuroscience. And you can now see if you plot some of these here, if you take a closer look, this is the way the sigmoid function looks like, and you will see that it flattens out when you go to large values of the input z, the argument. The step function is another possibility. If you take the sine function, this is this function here, which you could then use to set up the tan h function later. You have the rectified linear unit where you would put the activation function to 0. This normally gives some problems, so it's something which is called the modified rectified linear unit, which has a small non-negligible component for z less than 0, and then it's just a constant. So your results will actually depend quite a lot on the type of activation functions which you use. And it's normal to test the architecture of the network as a function of the active type of activation functions. So what we are going to describe now is the mathematics of a multi-layer perceptron model. And we are going to set up what's called the backpropagation algorithm, because this is the central algorithm in all of deep learning methods. So whether you're doing convolutional neural networks for imaging, whether you're looking at the recurrent neural network or general adversarial neural networks, autoencoders, etc., somewhere you will encounter the backpropagation algorithm. So we are going now to look at the mathematics of a multi-layer perceptron network, or just MLP, or as it's also called, a feed-forward neural network. So let us now take a look at some of these properties. So one of the things which we're going to encounter is this backpropagation algorithm. And we are going to specialize to the case of a regression problem where we have skipped the 1 over n when we calculate the cost function. So our network is going to produce an output, y of I, and we want to compare that with the targets. So y of I is the output from the model, and t here is the target value which we want to reproduce. Now, let's now take a closer look at things and make a drawing of what is coming and how we are going to set up these different parameters. So I'm going to go back to the whiteboard. You will find essentially everything which I'm going to put on the whiteboard is going to be in the slides here. But let's slow down the pace a little bit and go back to the whiteboard. So if we look at the mathematics which we're going to develop, the first thing which we need now is to actually set up some of the notations which we're going to use. So we have a input layer. So we are going to set up a feed-forward neural network, or what is also called a multi-layer perceptron model, an MLP. So we said in the beginning that we are going to have a input layer, and this will have lots of input data. So there's going to be you're going to mark these nodes with these dots here. So there will be an x1, an x2, and down to some x of n here. So that's our input layer. Just to give you an example, suppose you have a figure which has 200 times 200 pixels. You're going to flatten this out, and you're going to have 200 times 200, which is equal to 40,000 input nodes. So if you have such an image, then you're going to need 40,000 input nodes. We will see that later when we come to the data set, which is called the MNIST data set. Then what we are going to have is a hidden layer. So this will be our first layer, L equal to 1. And this continues till we reach a specific layer, which I'm just going to label in a generic way as a label L. So these are the hidden layers. So we feed in to the different nodes which we have here. So you will find a set of nodes here. And this would have N1 nodes. And when you're setting up the architecture here, this number of nodes do not need to be the same all the time. This then feeds in, so all the nodes are connected. And this feeds into the output layer. And we label the output layer with an uppercase L. So this is now our output layer. All these are just hidden layers, and we have a given amount of them. And the reason why we normally call this deep learning is that if you make the network deeper and deeper, then that's where you have the name deep learning from. So you're trying to learn a network which has a deep, deep set of hidden layers. So we have all the hidden layers here. And the hidden layers, they all have a given number of nodes. And you can play around with that. So the model complexity in this case is going to be defined by the number of hidden layers and the number of nodes you have, and obviously also the type of activation functions which you opt for. Then at the end here, you produce some output, and let's call this y. And this is now compared in a cost function with the targets. So I'm just going to mark that with t, being now compared with the output from the neural network. And this is the basic setup. So let's now single out a specific node here. So we are going to pick node J. So we are going to label the input to this specific node for ZJ of L. And that is going to be given by the sum over I equal to 1. And then it has the number of nodes from the previous layer. There's going to be a weight matrix. So we are connecting the different nodes, the Wij. And this is now given for layer L. So I'm putting an L as a superscript here, which means that this refers to the hidden layer L. This is multiplied with the output from the previous node AI for layer L minus 1. And then there is a bias, which we call Bj of L. So this is now the output from node I in layer L minus 1. So we are now summing over all these possible layers, now all the possible nodes from the previous layer, and they all feed in to that specific node which we have singled out here. Now, this specific node here produces an output. So this is now input, and then we have an output, which we are going to label as an Aj of L, and that is given by this specific activation function which we have chosen, CJL. So this is about the kind of notation which we are going to need. So the quantities Wij, L is a weight, which connects node I in the previous layer with node J in the new layer. And then we have the terms B of J of L, which is something which we're going to call the bias. And this is a quantity which is always added there, so we can ensure that we are going to get a result which may not be equal to 0 when we train the network. We are going to look now at a regression case. Later, we are going to see how we can change this to a classification problem. So we will specify now the mathematics which we're going to do to a regression case. We want to fit a function. So that means that our cost function, which depends on these parameters theta, which is now given by the weights, I just write this in a generic way, and the bias is B. This is a function which we are going to define to be now a sum over I equal 1 up to n. I have my outputs, y of I, minus my targets, squared. And remember now that these quantities here, we can rewrite them in terms of the outputs from the output layer. So this is going to be given by an AI of L minus T of I squared. So this quantity y of I, the output, is now given by the output from node I in the output layer L. So if we now look at what we need to calculate is now the following. So let's now also specialize to a specific activation function in order to make life a little bit easier. So this quantity is given as the output from node J in layer L, and it's given by 1 divided by 1 plus E of minus Z J of L. So this is the sigmoid function. And this is one of many possible activation functions. So there are going to be two basic steps, as we discussed before the break. We're going to have a feed forward stage, and there's going to be a back propagation stage. And the back propagation algorithm plus the gradient evaluation forms the basic mathematics. So the back propagation algorithm gives us the analytical expressions for the gradients at every single layer of the neural network so that we can actually train it. So the back propagation algorithm, or backward propagation, or just back propagation algorithm, propagation algo, gives the expressions for the gradients. Of a neural network. So that when I say over neural network, that means the gradients for every single layer in a neural network. So what we are going to do now is simply to set up the calculation of the different quantities which we need. And we are going to now, let me just bring this up here to set up the backpropagation algorithm, which is the central algorithm in neural network calculations. So we have defined this quantity z, which we put up here. So let me just remind you of that one. So this is one of the central quantities. Then I have defined this as the output from the previous layer. So it means that this quantity which you see here, this one, is actually equal to this activation function without us having specified it, but we are going to use the sigmoid function in our specific calculations here. Then what we are going to need is to be able to calculate the derivatives of the cost function the cost function with respect to the weights and the biases. So what we are going to need now is to have dc dw, I'm going to write it like this, equal to 0. And then we also need dc of d of b, which are the biases. So we are going to need some expressions. So let me give you some of these kind of quantities which we will use now in setting up the backpropagation algorithm. So these are kind of aiding quantities which will help us in setting up the final algorithm. So we need now an intermediate step, which is given by this quantity here, dwij for a specific layer. And you will see why we need them. So if we now look at the expression which we had, if we go back to z, which is defined here, you see now that if I take the derivative with respect to this specific weight, then I'm simply left with this quantity here. If I then take the derivative of this quantity with respect to this quantity, then I'm obviously just left with that quantity here. So let's just collect these two intermediate steps, which will turn useful in the calculations here. So we will have an AI of L minus 1, and you can see that immediately from that equation. And then I need a DZJL with respect to the AI of L minus 1, and we can show easily that this is given by this quantity here. Next, what we need, and we have assumed now that we have an AJ of L, which is given by the sigmoid function. If you don't have the sigmoid function, you will need to calculate another derivative. And I will show you later how you can actually generalize these things. So this is defined in by this function. So this is what we call sigma of CJL. So another quantity which I need as an intermediate step is to be able to calculate this quantity of dc of j of L. And if you do the mathematics here, you will easily see that this is going to be with the sigmoid function, with this specific one, it's going to be given by CJL and then 1 minus sigma of CJL. Now we have assumed that we have a cost function, which is given by the standard mean squared error, which we put up here. So this is our cost function. So what I'm going to do now is to calculate the derivative of this quantity with respect to the weights and the biases. So if we do that, we will need these intermediate steps which we put up here. So if I now take d of c, and we are going, and this is a function of these parameters, and now we're going to look at this at the output layer. So we're going to look at L, uppercase L, which is the output. So we take the derivative of that with respect to the weights, and just using the chain rule again, this is going to be given by AJ of L minus Tj. And this is going to be multiplied with Aj of L with respect to J of K of L here. So these are all values which are evaluated at the final layer. And now you see that one of the things which we're going to need with the chain rule, we will actually need this guy here. And then we're also going to need this quantity here, because we're going to use the chain rule. And we can actually show that this dAj of L with respect to Jk of L is going to be equal to d of Aj of L of dCjL, sorry, L, uppercase letter, of Cl, and dWjk of L. And if I use the sigmoid function, this is going to be given by Aj of L, the output from layer L, the final one, minus Aj of L, and multiplied with Ak of L minus 1. So if I put everything together, what I'm going to get now is the derivative of the cost function with respect to the weights in the final layer is now going to be given by Ajl 1 minus Ajl multiplied with the input from the previous layer, actually the output from the previous layer, that's more correct to say that. And this is then multiplied with Aj of L, which is one of the parts of the derivatives of the cost function, which also contains information about the targets we want to reproduce. And now what is common to do is to rewrite this parameter, which you see here, in terms of a new parameter, delta JL. So we would then have delta JL here, which depends on a derivative of the activation function in that specific layer, the output from the previous layer, and then multiplied with a term which depends on the type of cost function which we are having. So now we have basically this quantity here, and the thing which is interesting to note is that we can rewrite this, or rather this term here, as a derivative of the activation function. So we can rewrite this delta J of L, and we can make it more general, as the derivative of this function with respect to z of J of L. And this is again multiplied with the cost derivative of the cost function with respect to the output. So this is just a small manipulation which we can do. So this quantity here is now given by results at the final layer. Now, one thing which we can also show, so what we have is actually that d of c with the derivatives of the weights at the final layer is given by this parameter delta J of L multiplied with Ak of L minus 1. We can also show that this delta J of L is a quantity. It's actually not so difficult to show that this is given by CJL, which is again given by DC, dA of J, dAJL with dCJL. And with that, we can also show that this is equal to a dC of D, and I leave that as a small exercise to you guys to show. So if I collect everything, I have three equations now, which are going to be important. So I have the derivative of the cost function at the final output layer, which is given by this parameter delta J of L multiplied with the input from the previous layer. It's actually the output from the previous layer. I have my delta J of L is equal to the derivative of the activation function in the output layer, and they can change from layer to layer. You don't need to have the same function. And then I have a J of L. And then finally, I can also show that this delta J of L is equal to dC of dBJ of L. So these are equations which you can frame in and put under your bedpost and admire them before you go to bed. but we're missing one equation now. So the equation which we miss is when L goes to a given layer L. So what we need to calculate then is the following. So we would need to find this J at the given layer L. And as we've done before, this is going to be given by Cj of L. And we can now use the chain rule again. And this is something which we later are going to link with the automatic differentiation and the reverse mode. But now I'm just going to assume that I can sum over all the quantities from the previous layer. So I will have a zk of L plus 1. And this is multiplied with the derivative of zk of L plus 1. And then dzj of L. So I'm just using the chain rule, and I'm summing over all the contributions from a previous layer ahead of the one which we are looking at. Now, this is something which we can immediately rewrite as k of delta k of L plus 1. So if L plus 1 is the last layer, we have immediately that value. But then we need to calculate this derivative here of ck of L plus 1 of zj of L. And what we know is that ck of L plus 1, or let's just write it in a generic way here with a j, as we did before. This is given by a sum up to L here, and then we have a wij of L plus 1, and then I have an ai of L, and then I have the bias bj of L plus 1. And that, if I use this formula here, I see then that I can calculate these derivatives. So what happens then is that this dz of k of L plus 1 of dzj of L is actually equal to wkj of L plus 1 times the derivative of the activation function for layer L. So this is something you can keep general, and then just replace that one depending on the type of activation functions you have. So what we have then is that this parameter at a given layer, delta GL, for given node J, is now given by the sum of delta K of L plus 1, which we know. I have the previous weights as well, L plus 1, and then I simply need to calculate the derivative of the activation function Z, and I put a prime here to indicate that this is the derivative of the given activation function. So when you then have this, you can actually set up the gradients for the different layers. So what you have then is that the gradient W for these parameters, we can use that to set up an iterative scheme here, where we now have jk of L minus, and there's a learning rate, eta, multiplied with delta J of L of AK of L minus 1. And then I have my biases, which are updated according to the similar equation, minus eta of dc of d beta j of L, which is the same as bjl minus eta multiplied with this parameter delta jl. And that sets up our final expressions. So when we meet again next time, now we've gone through the mathematics of the backpropagation algorithm. When we meet next time, we're actually going to set up the algorithm, and we're going to explain the basic steps which are needed in the calculation of the algorithm. Then, after we've done that, we are then going to look at the link between this algorithm and the reverse mode of the automatic differentiation algorithm. But this ends this lecture now. And when we meet again, we are going to look at the explicit setup of a code which implements the feed-forward neural network with the backpropagation algorithm.